Good morning, this is Dr. Turner for Integrated Math 1. We're going to be finishing up first semester with 5.5, which is looking at growth and decay. Growth and decay are the most common examples of exponential functions. They're covered a little bit in Math 8. We see them again in Math 1. We'll see them again in Math 2. But these are real-world applications when we're modeling, particularly whether it's compound interest or your return on an investment, population growth or decline over time. These are really two big concepts that we see over and over again, and you'll see more so in your math career, but also in your science classes as well. So this is a pretty big one. These are word problems. Unavoidable. I try to ease up on you guys a little bit with the application, given COVID and everything else going on. But 5.5 does require you to do a little bit of word play and word problems. Now, that being said, remember, when you are answering a word problem, you should always answer in a complete sentence. So if it is asking you in words, your response should be in words. So keep that in mind. Again, trying to be lenient, but if we were in person, that would be something I would penalize you for if you were not writing complete sentences and just spitting out an answer. Okay. So let's step back for a second. To look at growth and decay, it's going to require us to look at our parent function. Now, we expanded our parent function a little bit when we were talking about transformations, right? We added in that h and k so we can move it up, down, left, and right. But your base parent function for growth and decay is y equals a times b to the x. So y equals a times b to the x. Now, we also talked about this a little bit with in earlier sections of Unit 5, where we said, okay, if you remember linear functions, which we spent a lot of time on this semester, you have y equals mx plus b, where m is your rate of change and b is your initial value. When you're doing word problems involving exponential functions, you'll find kind of a similar pattern. Now, they're not the exact same terms, but really you can think of a as being your initial value. And b is your rate in a sense, but we don't really call it that. But just for argument's sake, and so it's relatable, let's call it our rate of change, even though it's technically not. Most commonly, we'll refer to this as like a ratio or the multiplying factor. There's different terms depending on what textbook you're using, but it's kind of like our rate of change. Remember from 5.2, linear functions follow a pattern of repeated addition, or subtraction, whereas exponential functions follow a pattern of repeated multiplication. So we're going to be using this equation primarily for our purposes. Also, we're going to be looking at one that's slightly tweaked, which is what's known as the compound interest formula. Okay? And that is given as a equals p times 1 plus r to the t. For our purposes, we're looking at simple examples where your interest in these types of problems is being compounded annually, meaning you earn the interest every year. There are some tweaks we can make to this equation if we wanted to compound it monthly or daily, but because we're only doing annual interest for this section, we're just going to leave this as is. This is basically the same thing as our parent function, but instead of a, I'm putting p for your principal, your initial amount you're putting into an account. B is the rate of change, but we're writing it a little differently. We're doing 1 plus r. And then because we're looking at change over time, my input variable is t for time instead of x. Okay. Now, the reason I have the 1 plus r here is because in the real world, not everything is as simple as doubling or tripling. Sometimes you do end up with a percentage, and therefore we're not going to have a whole number for our b value. It's not going to be a 2 or a 3 there always. Okay. And we'll see that here in just a second. Let's start out with a couple easier examples. And I could write out the words for you. But let's say I have an initial population of rabbits. Say I have 20 rabbits to start out, and that population triples over time. I want to know how many rabbits I'm going to have in 5 years. Okay, so when I have something simple like doubling or tripling, then I can just write a whole number for my b or my 1 plus r. Tripling is 3, right? So I have an initial population of 20, and it's going to triple every year. I said, how many am I going to have after 5 years? So my t is going to be 5 for 5 years. I do want you to be able to plug in the values into the correct variables, so I would expect to see this on your work. But once you have it set up, then it's just calculator work, especially for a lot of these that are going to involve decimals. So I would go in, I would pull up my calculator, keeping in mind rules of operation, so 20 times 3 to the 5th power, and it'll spit out the answer, 4,860. So once you set it up, use a calculator, and then again, my expectation is that you are writing a complete sentence. So there will be 4,860 rabbits after 5 years. It doesn't have to be a long sentence, but I expect it to be a complete one. So don't worry about length, just make sure it's a complete sentence. And let's make that a little bit bigger so it's able to be seen. Let's go 26. There we go. So again, doesn't have to be a long sentence, just a complete one. Okay. So I see your work. You wrote a complete sentence. Perfect. Now that only works when, again, I'm using terminology like doubling or tripling. If I am increasing by a percentage, then I'm going to need to use this second formula down here. The a equals 1, or a equals p times 1 plus r to the t power. Okay. So let's do one that looks like that. And just for argument's sake, let's say I put in and I'll change the font here because it defaults to be super tiny, but an initial investment of $10,000 earns 3% interest over 6 years. What is the total in the account at the end of maturity? Meaning after the 6 years, how much is in that account? Okay. And again, let's make this a little bigger so we can actually see it. And this is kind of what a problem would look like on your test. Okay. So initial investment, $10,000 earns 3% interest over 6 years. What is the total in the account at the end of maturity? So we're solving for A here. So I'm going to plug in everything else. P, again, is your principal balance, or your initial value. So I have $10,000 here. And then it is 1, I'm going to plus or minus something, and it's for 6 years, so T is 6. Now, the reason I have that 1 there is that imagine if you multiply the 10,000 times 1. Right? 10,000 times 1, or anything times 1, is itself. So 10,000 times 1 times 1 times 1 times 1, even 6 times, it would stay the same. So if I am increasing, if I'm earning money, then I would need it to be above 1. And if it's declining or decreasing, then I would need it to be less than 1. Think back to when we were graphing and we looked at models of growth and decay. Right? Greater than 1 shows that growth curve. Decay is between 0 and 1 and shows that decay curve going the other way. So I want to add 3%. Okay, very common mistake. Students will go in here and just say, okay, well, it's 3%, so 1 plus 3. But that's not how percentages work. Remember that percentages are parts per 100. So if I have 3%, I can't plug in a percent into an equation. I need to convert it to a decimal. And this is middle school, a middle school skill. But the rule is if you want to convert from a percent to a decimal, you're going to take the number, 3, and you're going to move the decimal place 2 to the left. Okay? And then if there are any spaces, which there are here, then you would need to fill in a 0. So your equation should be 10,000 times 1 plus 0.03 to the 6th power. Again, very common mistake. Students will put 3 there, or they'll put 0.3 there. 0.3 is the same as 30%. It needs to be 0.03. Move the decimal over twice. Okay. All right, so now that I have my equation set up, it's just a matter of doing the calculator work. So go into Desmos, 10,000 times 1 plus 0.03, raise that to the 6th power, and I get $11,940, 0.5229653. Now, again, also a common mistake. I will see students write this 11,940, and let's write the whole thing, 0.5229653. The problem with that is that we're talking about money here. And so when you're rounding, you should be rounding to the nearest cent, right? 100 cents in a dollar. So I want to round to the hundredths place because I'm talking about money. So it's very important to pay attention to the context of the word problem. So the correct answer here would be $11,940.52. That is my correct answer. Am I done? No, because it is a word problem, so therefore I need to write it in a complete sentence. So again, doesn't have to be a long sentence, but it needs to be a complete one. So I'm going to go in, I'm going to type, and let's see if I can change the font here before I start typing away. There will be $11,940.52 in the account after 6 years. Not a long sentence, just a complete one. And we'll make that a little bit bigger, a little easier to see. That's it. Okay. So pay attention to your vocabulary. It's not always just going to say like plus or minus. Like in number 2, for instance, we had earns. So if you're earning money, that means you are gaining. So there should be a plus there. So earn, adds, interest, profit, any of those types of words, we should be thinking addition. If I have something that is decay, depreciate, declines, loss, any of those types of words, I should be thinking subtraction. So let's see, let's do one more. And put in box. So it says 26, I think, is working for us. So, baseball card, originally purchased for $1,000, and it doesn't have to be a nice even number, but I try to make them to start out with. Depreciates by 5% over 10 years. What is the value of the card after 10 years? So again, that keyword there is depreciate, which means that the value of the card is going down. So when I go to write the equation, it's going to be subtraction here instead of addition, right? And some books will write plus or minus to show that it can be growth or decay. So I have A equals 1,000 times 1. Again, this is subtraction because it's depreciation, and it's 5%. So if you need that scratch work again, 5%. Move the decimal twice. Should be 0.05, not 5, not 0.5. It has to be 0.05 or you're going to get a wrong answer. And then I want to know what its value is over 10 years. So there's my equation. I would expect to see that in your work. And then you just do the calculator work. 1,000 times 1 minus 0.05 raised to the 10th power. Remember, this is money we're talking about, so I need to round it appropriately. So I'm going to take that. I'm going to round to the nearest hundredths place. So I get 598.74. Okay, once I have that, again, complete sentences. The value of the card will be $598.74 after 10 years. And that's all there is to it. If you guys need help, please reach out to me, attend office hours. Otherwise, have a good day, and I will talk to you soon. Bye.